All right, so we're going to continue on. Here's a example, it's a rather involved example for a problem out of Shigley with shaft design. So we have this double reduction gear, and I had someone in class suggested this was a difficult drawing to quite get their head around. So I went ahead and made it into SolidWorks. Hopefully you can kind of understand a little bit better that this gear originally is actually onto the side over here, right there, and it's driving gear 8, which, oh, excuse me, it's driving gear, I called it 2. They didn't number it. Those were my numbers next to them, which is the 20 inch. So that's the diameter right there, the 20-inch gear, which is on the same shaft right here, on the same shaft as gear, what I labeled as 3, and 3 is driving what I've labeled as 4 right here. So it goes from a 4-inch diameter gear that's driving a 20-inch diameter gear. That's this guy right here. And that is on the same shaft as a 8-inch diameter gear, which is driving a 24-inch diameter gear. And once again, it looks a little bit like this right here. All right, so I've kind of made it up and kind of in a little isometric right over there, but also the other different views so you can get kind of understanding. So hopefully that makes it a little bit more clear. They give us a bunch of instructions and information. First thing they said is that the motor provides 2,500 inch-pounds in speed to this guy right here. Right, so it's they're breaking this apart into stages, and this is the guy right here at A that it's happening. So it has a power and a speed. Now, we don't know much about gear trains at this point. There's a later chapter, I think it's chapter 13, where they go over. But we can establish what the force must be on this gear onto that gear, right? So those things we can tell. Reading on more, we have a 20-degree pressure angle. That's fine. And we're going to use this material. And we have a design factor of 1.5, and we're going to base that on yield strength and use von Mises. So we're told to sketch a general shaft layout, and we're told a bunch of things. We're going to design this thing. And I also say do a cost estimate and create an Excel spreadsheet to assist with the design so you can repeat the calculations. We're not going to make a really thorough Excel. We're going to make one to just kind of help us out a little bit. Okay, so here is the where we're starting with. First thing I would do is I would go with this gear right over here. This one over here is this gear, gear 1. And we're going to put a torque onto it, torque TA. How much of a torque? Well, we'll do the sum of the moments. Well, we calculate the thing out as, I don't think I did that on here, and I should have. But that initial torque that we're going to have, excuse me, let me see if I can find my numbers over here. Actually, I have it on another sheet of paper. My initial numbers are not calculated right here. Where did I calculate this? I don't know. Must have calculated somewhere. Oh boy, this is not good. And oh yeah, they gave us 1,200. I'm sorry, they gave that to us, right? That was part of the problem. They told us that this was 2,500 right here. So because they gave it to us, I don't know why isn't that showing up here? Come back. Let me get just glad. Start up again. There, right there. Okay. All right. So using this first FBD that I've created, we can find out what that force is based on the torque they gave us. They gave us a torque, TA, so we can find out what I'm calling 21Y is. What do I mean by that? This is the force of the gear 2 onto gear 1. So I'm calling it force 2 1, and it's in the y direction. And based on the radius, which is 1/2 of the diameter, we're able to find this value, 1,250 pounds is what this force has to be. But that also has to be the force of gear 1 onto 2, right? They're equal and opposite from each other. These two are equal and opposite from one another. Okay, so we could also, by the way, while we're there, we can also find the radial force, which is just that tangential force times the tangent of the pressure angle. Now we can go to this next FBD with both of the gears in place, and we could find this unknown force, because we have this force now, and now we can do, using the sum of the moments, we can balance them out. So you can see that it's the tangential force right here times its radius minus this tangential force times its radius. And that's what we have. So we can find the unknown force, calling it F23Z, the gear of the force of gear 4. Oh, this should be labeled. No, that's fine. That's labeled correctly. This is gear 4 right here. Gear 4 is working against gear 3, right? So that's why that's gear 4, 3 in the Z direction. I got that correct. So I got 3,125. Now we can get the radial one just by, once again, multiplying it by the tangent of the pressure angle. And then lastly, we have a bunch of forces that we needed to know. We were able to find all of those forces in between the gears that are being placed onto this intermediate shaft that we're looking to design. We also want to get the torque while we're here that's going to be in between right here. It's not the same torque that was like placed in right there, right? So this is like where a motor is putting torque into this piece, but now we're going to have a different torque in between the two. So we split the gear, and I decided to just use this one right here, right, to split those apart. And so that is what my FBD is right there. So splitting it apart, we can find that hidden torque that's on the inside of shaft B, and we find that it's 12,500. One thing we can think of it as that this gear was 4 inches in diameter. This gear was 20 inches in diameter, so it makes sense, perhaps, that we were able to get a 5 times increase. So we had 2,500 inch-pounds in, we get 12,500 inch-pounds out. We've reduced the speed and increased the torque. Now we go, and here's the summary of those forces that we just got. Let's apply them onto the 2 different views, in the XY and in the XZ, and put those on, and then find these reactions. So some of the first things we need is these reactions. We should be already able to do this. Nothing new. So we get some of the moments about C, and we're able to find the reaction at dy. Some of the forces in the y direction, put them all together, and now we have the reaction at C in the y direction. Do the same thing over onto the other shaft, and taking the sum of the moments about C and about the y-axis, and we're able to get the reaction at D in the z direction. Some of the forces in the z direction, we are now able to get the reaction at C in the z direction. One thing different we haven't done before is we would like to have the total amount of reaction at C and the total amount of reaction at D. If you take a look, we have in one plane, we have this. If we're just taking a look at C, we have an upwards reaction here, and then if you take a look at C in the z direction, we have a upwards motion right there. And so we have a resulting diagonal motion right there. So we want to take the sum of the reaction in the y direction and the sum in the z, the square root of the sum of the square, and we get a magnitude, a total magnitude of the overall force that's being placed onto the bearing, which we can also think of as backwards as the force of the shaft onto the bearing. So we need to design the bearing, and in our abbreviated catalog in Shigley, it goes in kilonewtons. So we're going to apply a factor of 2 on top of that when we go to look at it. But we're doing that mostly because we would like to know what the diameter of the bearing needs to be in order to use it in our shaft assembly. So we're going to jump the gun without learning much about bearings. Just know that we have a catalog, and for some reason we're going to multiply it by 2. And so we're here, but here's the load that's on it. The same thing with D. We'll notice that D is less than C. So there's a little bit of practicality involved in using the same bearing for both ends for a single shaft. Easier to buy it. Don't have to buy two different types. Buy one, just 2 of the same type. But also for the end user, they usually have to keep spares, and it'd be easier if you would have the two bearings of the same kind. All right, so now we have our shear moment diagram. I've jumped the gun. You should be able to do this. So I put in the values so we could look at them as I highlight right there. So there's the values we just found, although we had to subtract out the one in the middle so we can figure out that what that little segment looks like. All right, so here's the reaction. Here's the difference between the reaction and the force on the left, and then here's the reaction here on the right. And now what we want to do, instead of just finding the center of the gear, which is what we've done before, we're actually going to look at ends up being 6 places, so we need to get 12 values. So this is sort of repetitive. So maybe we could set this up in Excel, but I'm going to go ahead and do this essentially by hand and just walking, going from left to right. By the way, a little proportional, maybe, kind of. This right here is only 1 inch between D and the edge of here, right? Let me put my screen down into my tablet mode so I can write better. All right. So right from here to here in our original problem is 2 inches. From here to here is 3 inches, and then this is 6, right? So the whole thing is 11 inches long. I'm saying this gear, it looks pretty close to being 2 inches wide. So that only remains to be 1 inch in between these two. And then, of course, there's 1 inch right there. And then 1 inch right here. Right? And then in between these two right here, that appears to only be 4 inches, although I might have messed this up, something up later on. Okay. But we'll keep going with it. And then 1 inch right here, and then 1 inch right here. And then what's left is going to be 2 inches in between here. All right. All of these details are necessary for us to be able to think through what we have to do. But I think I just messed something up right here, unfortunately. Maybe I'll get the right number, but I think what I have written down is wrong. So anyway, I find this first point right there. And then I find the second point right here. So it's going to be this guy right there, right? Just 1,054 times the 3 inches to get that value. This one I need to subtract a little tiny bit because it's sloped. You notice that it's sloping downwards right there. So they're not too much different from each other. Then I find this piece. I decided to go from here. Oh, no, I know what I did. I decided to go from here to there. So I got it right. Okay, so I did right 5 inches. So you notice that I used the center one, this guy right here first, and then I went over that way from that. So, okay, good. I used 5. I thought maybe the 4 was incorrect. And then I decided not to keep going from left to right. I decided to go right to left. So this is going from here to right there for this value. And then lastly, I went from there to there for that last value. So that's the kind of the big idea. I know it's you've done something similar. This is just slightly different in the amount of spots that we want to get at the moment. And the same thing true over on this side right there. So you can hit the I believe button. That all of these values right there, that was our goal from the shear moment diagram, to place those into context. All right, so here's some things we're going to have to start looking things up and making some decisions. Some of the first thing I might want to do is pick out what my bearings are going to be. Right. But I would also mention a sketch like this can really help you think through the parts. I've already made a decision, and this is going to be kind of awkward. That I am not. I'm going to make a step here, but I've decided not to make the additional step in between the gear and the piece. Right. So this, because this right here is going to be a 1 inch. Let me see if I can say this the right way. This right here is 2 inches. Okay. And right up to the gear, I didn't quite draw it quite correct, but so we'll have to think through it, right? So I'm sorry to have it hemmed and hawed onto this. All right, so this is like going to be 1 inch right here, and this is 1 inch right there. Is that true? Yes. So this right here, what's left is 1 inch, but we don't quite know how big the bearing is. So we're gonna go look and see what bearing we want to pick, and that bearing comes in a width. So we don't really have any choice, but whatever's left over would be like this amount right here. So we could cut off and make a cut this off right there at the end of the gear, and then make this somehow make a step of a very short amount. But that doesn't quite make sense when we go to see how small that is going to be. So we could just stick to stick to a recipe, but we could also use some common sense. So let's go take a look and see what kind of size of a bearing we would need. Let's see. I got to go back to where we came right here. Right. So our goal is to use that size and to from that size pick a bearing. So we're going to I'm going to discard everything because it's all just a bunch of marks. All right. So our size was 11.48, and we're going to use a factor of 2 times 11.48 to establish. So that's going to end up being 22.96, basically 23. So we go into Shigley, and chapter 11 is the roller bearings, and we don't go far into it before we see table 11.2. And this is a simulation, or even just an excerpt of a bearing catalog. And if we're going to use the deep groove bearing, so the deep groove bearing, and we're going to use what's called a C10 rating. We don't need to know what that is just yet, but we're going to use it and see if we can find a bearing that will sustain 23, I believe I said, 23 kilonewtons. So we found one right here, this 35 millimeter, that can handle it. 35 millimeters, and it can handle it 23 kilonewtons. So that's what we're going to choose. Now this is the bore. This is the category. That's how they're cataloged. The bore size, which is the diameter that we're going to now have to make our bearing. So that's a 35 millimeter. We could divide by 25.4 and find that it's 1.378. If we find a U.S. catalog and they're made this way, that'll be 1.375. You can count on it. And then the width of this is 17 millimeters, 25.4 divide, that comes out to like 0.669. All right, well, let's just go ahead and tell the people, even though we're going to stick with U.S. units because that's what we've been given, and we're maybe a U.S. factory, and that's the way that we work. But we'll tell them that we're going to use a 35 millimeter bearing. For some reason, during class the other day, we went up to the 40 millimeter, which might be okay. But let's just stick with the one this one for right now. So the big information that I'm going to write down on my thing is a 35 millimeter bearing, and the width of it is 17 millimeters. All right, we're going to lay that out here in a moment. All right. Next, I want to maybe make some Excel fun. And I'm going to put my laptop computer back up to this way and put together some information. Maybe I want up here on the left-hand side somewhere. It's good to document things. So I would go like yield strength, and I would look that up in the book and find that the yield strength for the steel that they had specified, which was it was 1020 cold drawn steel, 1020 cold drawn steel. Up here in the appendix would be 1020 cold drawn steel. Here it is, 1020 cold drawn steel. You have a yield strength of 57 right there. You can't see this because it's too small. 57 KSI yield strength. So we'll place this in here, and I'm not going to go make the subscripts all pretty. Maybe I would do that later. And I go 57, up 57 KSI. This is an input. I'll go design factor. These are inputs, and D equals, and I'm putting these over to the side. We were told that we're going to use a 1.5. Doesn't need any units. I think that's all I'm going to put over here in my initial piece. I'm going to go over to the right a little bit for some of these things. I decided on mine to label them lowercase positions, A, B, C, D, E, and F. You don't have to do that, but it's, I don't know, I find it's convenient to, let me make this bigger. Convenient to have some kind of organization. So I'm going to go MZ is equal, MY is equal. And I'm going to fill all of these in that I just created down over, that I just displayed here in this figure, right? So all of these different moments, I'm going to go from left to right, and I'd call them A, B, C, D, E, F. All of those locations. That's the big idea. And if you wanted to, and in this case, I could be like a little, sometimes what I'll do if I can, and I need to, and it'll be helpful, is I'll actually paste stuff into my Excel. One really handy thing to do is either paste as a picture, or I found it even better, it comes in if you paste special and use an enhanced meta file. You can make it look better by right-clicking and formatting and doing a fill, where you fill the background, but make the background white. Boom. All right. So some of these things can help me keep track of things. I might not even keep it in there, but if I was trying to communicate to somebody in my Excel, this is what I would do. So I could I could put all of those values in. I might pick another color, meaning that like it wasn't given to me. I had to calculate it someplace else. So I'll pause a second while I fill this thing in. Okay, so I put all the values in, and you didn't have to sit there and listen to me talk about them. All right, so let's make the square root of each of these pieces squared. That's squared plus, whoops, that's not right. I have distracting people outside my office, loud mouths. They're about to get their ass handed to them in a second. All right, and boom, I think I got the right answer. No, why did I do? Why is this answer different? Huh. Let me see something here. All right. That doesn't make any sense. Why is my answer different? This is what I'm doing right now is I'm looking at another version. Oh, I see. I transcribed something wrong. I said 4,710. Yeah. Okay. No, it was over on here that I did it wrong. Maybe I didn't. Okay. Anyway, I'm gonna trust the one that I have. So I got that right. Bring them all over. Okay. So here's the moment that the thing has to survive. Right. I also need to have the torque that's being placed onto each of the pieces. Now, interestingly, there is no torque at this little spot. And let me point out the spot to you on this. That is this spot right there. That's the spot we care about. This is also a spot we care about, and this is also a spot we care about. So there's no torque. There's torque between. There's torque right here, and there's torque right there, but there's no. And there's torque right here, and there's torque right here, but there is no torque on the shoulder that would be there, except I'm about to choose not to do it. All right, so the torque that we're transmitting here is 12,500. Boom. And we're going to put it at all these places, but make it 0 right there and 0, whoops, 0 right here. Now for now we also need stress concentrations. Now we could technically get away with this design for ductile material without having this involved, right? But we're going to be cautious and go ahead and use the stress concentrations. For ductile materials, you don't have to consider stress concentrations. But in a cautious manner, we're going to go ahead and use it. So with this, we're going to look that up over here in Shigley. They have a section in shaft design about stress concentrations. And because we don't yet know the diameters, we're going to have to use an estimate. In a second, I'm not sure, this video is already too long, but I'm going to go ahead and do it anyway. We need to, I would like to build it in Shigley, build it in SolidWorks and see what the dimensions look like. Because we have a choice between sharp and well-rounded fillets on the shoulders. And we have to make that decision. We don't have much information about the keyway. So I'm going to go ahead and stick with an end mill key set type of thing using 2.14 and 3. So we have 2.14 and 3 that we know we're going to put in right here. 2.1 and short attention span, can't remember it, just 3. And we're going to put that in both places right here and right there, right? At what I'm calling B and E, which is directly on the center of the gear. Now to the left of the gear, we have to decide. Now, I had in class, I think I used well-rounded, and that's probably going to be okay in that spot. But when it comes to this spot right up against the gear, where the gear is this spot right here, where the gear it's got a tight shoulder. We actually have to go pretty high, pretty fine. I can demonstrate that in SolidWorks. So in here, I'm going to go ahead and use the, it might even be in our best interest to just grab this table and put it in there while I'm trying to, whoops, what happened there? Dude, no, I want this, okay. Boom, okay. So I will use the well-rounded here, no big deal. 1 point, excuse me, yeah, 1.7 and torsion 1.5. But, and that's true from here, which we don't even, I had already decided we don't need that one, that we were going to get rid of that step. But here, between this one, we're going to go with the much more, the higher one, the 2.7 and 2.2. Okay, so we could keep that there, put it over to the side, arrange it, make it look prettier later on. Now what we're going to do is, let me go back to my notes up at the top. And I thought I had it here. All right, so I only need, I'm just going to reference, I'll just copy that and place that into here. I should paste okay. Well, I tried to paste it into a cell. Let's see, can I paste it here? Also tried to paste it into a cell. I'm going to paste it as an image. Here we go. You go paste special and do it once again as an enhanced meta file. Boom. All right, so now we can actually, it'll look correct. So we're going to go right in here, and this is where the diameter is going to be placed into. And we will find it go equals parentheses. Let's just go with it. Okay, so 16 times my design factor, but I have to go, whoops, no, I didn't want that one. Let's go to F4 right there. F4 made the dollar signs around it. Divided by PI divided by, now I need to remember that my yield strength, which I also need an F4 next to, right? So I get the dollars. We have to multiply that by 1,000 because it's in KSI. Right, so that's done with up to right here. Now we're going to go times square root and 4 times parentheses, I'm going to go KT times moment, total moment, close parentheses, raised to the 2. So caret 2, then plus 3, right in there, 3 times open parentheses KTS times torque, which is 0 for this position. That's okay. We're going to need it for when we copy it over. Raised squared. And then I think my close parentheses, this is an important one, right there. And by the way, as you're closing it, so I just backed up a little bit, look for this guy to highlight a little bit. Boom, right there. And I think we can close our parentheses, boom, yep, and you can see that that one highlighted, so that did match. Now we want to raise it, open parentheses, 1/3, close parentheses, boom. And so now we have 1.329. You recall that, okay, so that's what we're saying is the minimum diameter for, let me go back to my little diameter, for this diameter shaft right there. It needs to be, that's the minimum it can be. Remember that our diameter for our bearing is 1.375 or close to that. So So this is in the same range, but we do need to have this criteria that we had established of a ratio of somewhere between 1.2 and 1.5. Let's see if we can find that type of thing. Is it right in there? No, where did we? I think it was earlier when we were talking. Yeah, right in. Nope, it's in layout. I swear we had it in there somewhere. I don't know where I would have put it into the presentation, but I could just tell you to do it. There you go, rule of thumb. A rule of thumb for step shafts used between 1.2 and 1.5. If you don't believe me, it's actually discussed right here, 1.5. They're saying that this is just a typical range. Maybe you come up to here. Yes, right there. Most of the time, it typically says 1.2 to 1.5, so that's going to be one of our rules to make. So that's why we're going to think through that as we pick our diameters. Let's see what happens, and if we did this correctly, it'll keep referencing these cells up here, but it'll change the cells. So we could copy and paste, but I like to drag that little bottom corner thing over. Something I didn't do that we should also put in the units everywhere, just to communicate to people in the future, and it could even be ourselves. No, I don't want inch pounds. I just want inches. So it likes to try to be helpful, and ends up not being helpful. I'm going to reduce the number of sig figs right there, just so I could get kind of a better idea. All right. So some of the things we have to make when we make our decision, right? And we have this sketch that we're kind of looking at. I'm going to draw on top of this here for a second. So let's write on it right now, even though it's probably not the easiest thing to do. This is 1.3. What do you say? It was 35 millimeters, and 35 millimeters is 1.378. Right, for our calculations, say, let's just write it out this way. Control C, Control V. All right. Well, that was kind of weird. Okay, but we can tell from there. 1.33. 2.135. This says we're going to be 2.013. This guy says 1.920. This says this has to be 2.075. We have a step here that I haven't even bothered to draw yet because I decided it was too short to even bother making. But that would have been the 1.101. And then, of course, we think we should use the same bearing, so 1.378. Now, if you've just built this thing this way, that would be kind of stupid looking. But of course, obviously, for one thing, these two are that's the same port right there. So you should really just base it on the larger of the two things. And we want to use preferred sizes. Our preferred sizes are located in Shigley in the appendix. Close you down. A17. So in A17, we went way too far. A17, we see the preferred sizes. We want to stick with those as close as possible. We can have a little bit of wiggle room, but so I'm okay with going by eighths, and then sometimes even going by 16ths if we're small enough here. We take a look at the biggest diameter is 2.135. So I take 2.135 and I say, well, that's probably 2 1/4. We could, let's see. No, we can't go 2 1/8. That's 2.1 too far. So we made this decision, right? So our first decision is 2.25. Okay, now let's see to the right of it how big we're going to be. 2.25, so maybe 2.25 times 1.2, 2.25, 1.2, boom, is 2.7 inches. Now, do we want to go, if we're going to base it on this, do we want to go to 3 or do we want to go to 2.75? Let's stick with the 2.75. I like that. So we decide that this is going to be 2.75. 2.25, 2.275. When we go to the right of this large section, is it better? We have in order to make this design, we say 2.075. Is that going to be a problem? I mean, we could make it 2.125, 2.125, but why would we want to? I mean, it kind of makes sense to just stick with the same one over here. We've already established that we're not going to make this step. So we want to double check this little end over here. Can 2.25 divide, so 2.25 divided by 1.378. 1.378. It's 1.63. See, we really would like that to stay within this criteria. Well, in my previous time that I ran through this and doing it live, we actually went up to a 40 millimeter bearing. And when we did the 40 millimeter bearing, we got 1.575 here. So there's an option right there, because that compared to the 2.25, that was 1.42 or 1.43, which was acceptable in our thing. We're kind of a little bit stuck. It's not the greatest reason to be making the bearing that different, but I think I'm going to go with it. I think we can make it so 1.429, which is 40 millimeters. We can stick with it right here. So 1.429. Okay, so lastly, let's decide. Okay, so this needs to be greater than 1.33, but it actually needs to be larger than this. It needs to fit between this diameter and that diameter with that same, the same 1.2 d over d between 1.5, right? So that's the rule that we're trying to stay within. So let's see what size would make sense of that. So let's first take the 2.25 and divide it by 1.2. Okay, we get 1.875. So 2.25 divided by 1.2. Just want to double check because I feel like I just said something that wasn't true. 1.2. Yes, 1.875. That might work actually, even though our preferred sizes are, it wouldn't show up in our preferred sizes. It's, it's right between, that's 1 7/8. It's right between here. You see the 7/8 is recorded back over there. So it's not, we probably have some leeway, and it's not a terrible size to use. I think it would be an acceptable size to use. So I think that's what we want to go with. Let's double check that over here with this size, 1.875, and divided by 1.429. Boom, we get 1.3. That's totally acceptable, right? So I think what we have right here is a design. So here's the actual design. Here's the D. And then we go actual. We can find out what the stress, what the yield, what we're going to say that the predicted stress is going to be due to this. But just as a means of keeping track of what we said we were going to do. We have 1.429 is what we're going to pick for that. 1.875 is going to pick for that. 2.25, pick for that. This is also 2.25, and in between those is a 3-incher. This one's going to be 2.25 because we're not even putting out to the. Actually, I think I'm actually writing down numbers that aren't correct right there, so I'm going to delete that out right there. Let's just leave it there. Let me take a look and do a quick SolidWorks. I placed a video. I was going to make a separate video for this, but it's Friday and it's 5:38, and I need to go home soon to my beautiful wife and lovely daughter. So let's make this continue this on, even though it's going to be way too long of a video. And let's see, we've already made it 45 minutes. No, let's continue on. I'll make a separate video for this. So this has been the decisions that we made along the way for the diameters that we're going to pick, and now we're going to lay it out into a drawing. There's already a video for this from 4 years ago, but this might be a better video than that one. Maybe. I don't know. Maybe not. I'll see you soon.